All right, we're good to go for the next talk, and I'm happy to introduce Albert Much from Leipzig, who will tell us about quantum entropies and quantum physics.
Thank you. Thank you for the organizers for this very nice workshop. Yeah, so the outline for my talk is a little bit connected to the former talk. I'm going to introduce the Bekenstein bound, say how one can generalize this to quantum field theory, which leads us to the notion of relative entropy. Then I will give you a crash course on modular theory, and I hope it will cover the basics so that in the discussion session we can also have some interesting questions. Then I'm going to define the relative entropy via the modular operator, and I will show you some applications to non-commutative quantum field theory. So the basic question is, what happens if we throw a hot cup of filter coffee into a black hole? Since it is a thermal system, it has some entropy. What happens when it goes inside of the black hole? And the answer is so for a stationary, non-charged, non-rotating black hole, the entropy is proportional to the event horizon area, which is in the Schwarzschild case just m squared. Alpha is some constant. Bekenstein did not really know what it is, except for the dimensions. 1/4 was then later calculated and proved by Hawking. And now now this thing stopped working. No, sorry. Okay, so there's a poor man's derivation, as Bekenstein calls it, for the Bekenstein bound. And it is basically, you consider a system outside of the black hole, some small mass compared to the mass of the black hole. You drop it in. This is a little bit, okay. And the total initial entropy, of course, is the entropy of the black hole plus the entropy of this small mass. Now, dropping it into the black hole, neglecting energy losses, gives us basically alpha m plus m squared. You have alpha m squared, which is again the black hole, and Bekenstein-Hawking entropy, plus 2 alpha big M times m plus m squared terms, right? So since entropy can never decrease, the entropy always increases, you just plug in SBH plus m minus S minus, and this has to be greater or equal to 0, and then you obtain the Bekenstein bound. This is the easiest, most heuristic way to obtain it. There are discussions about this. This is not non-controversial. There has been some papers back and forth between Bekenstein and Robert Wald and Unruh about the validity of this bound, but let's assume this bound holds. Okay, and sorry. So if the black hole is large enough to swallow the system, so you say this is somehow the system has radius r, and we identify E equal to mc squared, then you get for a system of radius r and energy, basically this Bekenstein bound, okay? So it's a universal entropy bound on physical systems. So although derived via the black hole formula, it should hold in general. And the question is, can our most fundamental theory, I mean, experimentally proven and theoretically found proof theory, reproduce this bound? And this is the question that Cassini asked himself. And the problem is, all these elements are ill-defined in quantum field theory. So neither the entropy is well-defined, nor is R, because I mean, what is R if you have a global energy? And yeah, the energy is ill-defined. Local energy densities have to be renormalized or have UV divergences, so they have to be regularized somehow. So none of the single elements in this Bekenstein bound is quantum field theoretically well-defined. However, one can ask oneself the question: how can we handle these divergences? And the naive application of von Neumann entropy in QFT, as I said, leads to divergences. This is because the QFT is a von Neumann algebra of type 3, which basically means that you don't have these trace class operators that usually you use to calculate von Neumann entropies. So Cassini won, by the way, the Horizons Physics Prize for this paper. And he says the physical origin, I mean, this is clear that the UV divergences, they come from vacuum fluctuations, and the entropy would measure all of that, and so on, calculate all of that, and thus it will be infinite. The solution is to subtract the vacuum contribution. So remember the right-hand side of the Bekenstein bound is entropy. We regularize the entropy by taking the entropy, the von Neumann entropy, with respect to a reduced density matrix of an excited state associated with some spatial region of interest, and we subtract from that the von Neumann entropy of the vacuum state, okay? And this should give us something finite. This is just an example for a vacuum density matrix where K is the local Hamiltonian. This is the example because from a dimensional point of view, this fits exactly what the right-hand side of the Bekenstein bound basically is. So it's just an example for such an operator. Sorry. So now we dealt with the left-hand side. Now the right-hand side is also divergent. And this has to be also regularized by subtracting off the vacuum expectation value of this operator K. And so the quantum field theoretical Bekenstein bound is this regularized version. SV is less equal than KV. Now, simple algebraic reformulations lead to this term basically being greater equal than 0. And this is nothing else than the relative entropy. And for those of you who don't know what the relative entropy is, or the quantum relative entropy, it has two key interpretations. Basically, it is a state distinguishability measure between the state rho and the expected state sigma, or it quantifies the unexpected information content or the surprise one encounters when one encounters the state rho while expecting sigma. Okay, and the relative entropy is always non-negative. So this can be proven for the von Neumann relative entropy very easily. And yeah, and the point is there is a mathematical framework that is well known to algebraic quantum field theorists till from the 70s that studies relative entropy, and it defines that in a well-defined and rigorous manner. And this is given by the Tomita-Takezaki modular theory. Okay, so let me give you a quick crash course here. The basic setup is you have a von Neumann algebra, you have a Hilbert space, and you have some cyclic and separating vector for this von Neumann algebra. Then the Tomita operator does nothing else than take some element of this algebra, apply it on omega, and it gives you the conjugate thereof, right? The adjoint. And S is closable and densely defined, thus it has a polar decomposition, and it can be written uniquely as this modular conjugation operator, which is antilinear and unitary, and the modular operator. And this is a very abstract notion that per se has nothing to do with quantum field theory, but one can apply it to quantum field theory and connect it to physics in a very beautiful way, basically by the modular automorphism group. So I just say this modular conjugation takes also the von Neumann algebra and gives you the commutant thereof, so all elements that commute with the von Neumann algebra. So you can generate this one parameter group of automorphisms. It leaves this von Neumann algebra invariant, and this is the way you do it with the joint action. And the state omega that you used for this theory is a KMS state with respect to this group. And KMS state, this is rather the technical definition, but it is basically a generalization of the principle of the Gibbs ensemble. So whenever you have a KMS state, you know you have a state that is in a thermal equilibrium. Okay, so that is the connection of this very abstract notion to physics, basically. And then there is a relative modular operator. I think, no, yeah. The setup here is very similar. You just have now, instead of one cyclic and separating state, two, omega and omega prime, with their corresponding vector representatives. You have a relative Tomita operator, which doesn't just give you the adjoint of A, but it gives you the adjoint of A and replaces omega prime by omega. Again, this can be uniquely polar decomposed. And then you have a relative modular conjugation and a relative modular operator. Now, why am I telling you this? The reason is that with these objects, you can define the relative entropy. And this has been done by Araki Ullmann, both, simultaneously in 1977, but in different papers on a little bit different approaches. And the definition of the relative entropy between two states is now very simple. It's just basically the vacuum expectation value of the logarithm of this relative modular operator. There are some special cases. So when the states are unitarily equivalent, then this formula reduces even further to a very easy form. And the name of the game in this business is to find out what the modular operator is explicitly for some quantum field theory and for some regions for this quantum field theory, and then you can really calculate the relative entropy. So let's do that. Okay. So basically, there was a paper, I think 77, the Bisonano-Wichmann theorem, where they gave an explicit form of these operators. And for the Rindler wedge, so you know the Rindler wedge, so when you have Minkowski, you take the right Rindler wedge, which is this wedge that is on the right, and there's the left Rindler wedge, and this is defined basically as follows. Then you take some local observables in the right wedge, and for those, the modular operator is explicitly given by the exponential of the boost operator, okay? So the boost generator, you all know, of course. And there is, of course, the KMS connection that the vacuum state is a KMS for the wedge algebra. And the modular group that implements this is generated by the boosts. And this is the most conservative interpretation of the Unruh effect, actually. Now, let's calculate the relative entropy explicitly. You have your reference state omega. You have your excited states that you generate by some unitary coherent excitation. And these operators are localized in the right wedge. So the support of this test function is in the right wedge. And then you can go through the calculation. So this on this is 0, and you can do this in different manners. And what you get out is basically that the relative entropy is equal to x1 times t00 dx. And this is nothing else than sort of this Bekenstein bound, right? Because this is R times the energy. Yeah. So this was the crash course on relative entropy and its connections. There has been a lot of works since 2008 and since 2019. Somehow the algebraic community has taken over. So there was a lot of works by Longo, so entropy of coherent excitations by Holland. He calculated this for chiral conformal field theories. Then Ishibashi applied this to black holes. Then there was some work also by Cassini, some other works by Holland and Faulkner, then by Eduardo D'Angelo about spherically symmetric dynamical black holes. And relative entropy. Pinamonti Ferch proved or calculated the relative entropy for a scaling limit of dynamical black holes. And also the relative entropy was then further generalized to curved spacetime by using what people call standard subspaces. Then there was some work by Relander and Ferch and myself about the relative entropy for fermion excitation states. So basically, we generalized the framework of the canonical commutation relations to the canonical anti-commutation relations. There was also some work by Freub and Papadopoulos and myself about the relative entropy in the sitter, because you can embed some patches of the sitter into a higher dimensional flat Minkowski space, and there this embedding respects the boosts, and then you know what the boost operator looks there like, and this is exactly the modular operator, and with that you can calculate the relative entropy as well. It turns out to be related to a Noether charge. Then Freub and Sangaletti did a generalization to Petz-Renyi relative entropy, so instead of just a normal relative entropy, you have this generalized one. Finster, Felix and Johnson, Lottner and Simon Muro myself, we did this, we connected this a little bit to fermionic entropies of causal fermion systems. Then Hollands and Longo did recently a paper where they provide a new proof for the QNEC, for the quantum null energy condition. And we also did this for the, we compared two methods. Felix and myself, one where you can use the reduced one particle operator for fermions, and one using the modular data, and they agree. And so there are many more works. I am just mentioning a few now. One can ask oneself the question, what happens if you apply this to a very conservative approach to quantum gravity, which is non-commutative quantum field theory? And I mean, this has been said already many times. Assume there is a minimal length under which, operationally localization of the space-time point doesn't make any sense. So you can introduce like some non-commutative scale. And this was done by Doppler, Fredenhagen, and Roberts. And the quantum field theory, then you can define actually a quantum field theory on non-commutative Minkowski space, which is given as this tensor product of the representation space of these non-commuting coordinates and some symmetric Fock space. And this can be then represented a little bit more nicely on the Fock space. This was done by Gandalf and Grosse in 2007, where they proved there exists a unitary map. And this is the normal scalar, free scalar field that you know and love, with the addition of these extra factors, where P, this big P is basically the momentum operator. So you encode the non-commutativity somehow in these highly oscillating terms. So for small theta, you can basically ignore this term and you get your commutative quantum field. So this is the nice thing about this approach. There is no problem on going to the commutative normal QFT, so to speak. The authors proved then that these fields are wedge local. So if you have a field that is localized on the right wedge and one on the left wedge, then these two are space-like separated and then they commute. With these fields, you know the modular data as well, very specifically. Sorry. Okay. And you can calculate now the deformed relative entropy, okay? So instead of using these normal commutative scalar fields, I mean, they don't commute, but they are defined on a commutative space-time, you plug in these non-commutative scalar fields. And since this is an interacting model, you cannot really give a nice expression to it, or at least I haven't found one in the last 4 years. But you can do a formal power series. I think I found a proof to show that this is analytic. But however, in essence, what you get out is the usual relative entropy, which gives you the normal Bekenstein bound by Cassini, plus some correction term that depends on theta. Now, if you go back to the original derivation of the Bekenstein bound, and say, well, let me say this is my original Bekenstein bound with this extra term, and you do not neglect the small m square term, okay? And you just do a coefficient comparison between this and the original one of the poor man's derivation of the Bekenstein bound. What you find out is that this constant that we usually identify with the Planck length is actually the Planck length. So in a sense, this is a quantum field theoretical proof of non-commutativity, or of the validity of that, and assuming that there is a non-commutative constant that you can relate to the Planck length. And on the other hand, you can also see this as so using Cassini's approach and just the normal relative entropy, you only can calculate the Bekenstein bound up to this m squared term. But using this non-commutative approach, you get the full picture, so to speak. Yes, and I think this is it. Thank you for your attention.